In Chapter 13, we'll be learning about kinetics. And kinetics are very important to the study of pharmacology, drug design, and biological pathways. This particular section is more quantitative in nature as compared to previous chapters. And distinctively, we'll learn how to use graphs to solve problems. Here's an example from biochemistry about how kinetics solves problems and tells us about pathways that happen in the body. This is the structure of cholesterol. And you get cholesterol from two sources. It can come from your diet, or in the case of humans, you can make it from much simpler molecules. And it takes about 10 steps to go from something called acetyl-CoA to cholesterol. And so there's many steps involved. Kinetics is the study of rates of reactions. So let's say I work for a pharmaceutical company and I'm looking to make a drug that blocks cholesterol synthesis. Some people make too much cholesterol. It's called hypercholesterolemia. And the feedback mechanism that's supposed to shut off the production of cholesterol doesn't work very well. So there's a whole category of medications that you can take. They're called statins. Right, so if I'm developing something in the laboratory and I want to use it as a drug to prevent cholesterol synthesis, I need to know the rate with and without the medication, right? I need to know what it is normally, and then it should slow down when I add the prescription medication to it, the compound that's going to block the production. So the only way that I can know that is to know what that rate is. We need to define some terms important to the study of kinetics. I've already made mention of the fact that kinetics is the study of reaction rates. Rate is the time needed to make a product, P. Order is defined as the effect of reactant concentration on rate. And we'll talk more about what that means specifically. The rate law is a description of the reactant and order effect on rate. So if we look at this illustration on the left-hand side, you have something that is a fast rate relative to a slower rate, fast versus slow. So in the left-hand side, we're looking for the appearance of the green molecule. This is represented as C, the product. And so in the first box, that's time 0, or initial time, there is no green product. And then in the second box, there are 4G for green. In the third box, 1, 2. In the second box, after time 0, we have 2P, and then in the last one, 3P, but it is not gone to completion yet. We could figure out about how much time it would take, but it would take 47 seconds plus some amount of time. This reaction is between hydrogen gas and iodine solid to produce hydrogen iodide. We would have 2 of those. So I could look at rate with respect to the time for hydrogen or iodine to be consumed, or time for production of HI. Now notice in the balanced reaction we have 1 H2, 1 I2, and 2 HI. These mole ratios will hold true when we're talking about the appearance and disappearance of reactants. As we look at this graph, we notice that it shows the relationship between hydrogen and hydrogen iodide. That is, hydrogen is being consumed and hydrogen iodide is being produced. So we can write rate in terms of either the reactant or the product. In terms of reactant, it's negative change in reactant concentration over the change in time. It's negative because the amount of the reactant is going to be decreasing. Anytime you see brackets, this represents molarity or concentration. We could also write rate in terms of the production of product over the change in time. We also have to include moles in here to represent the relationship. In this case, we have 1 hydrogen for every 2 hydrogen iodide. Okay, so if I'm specifically writing for this reaction, rate is equal to negative change in hydrogen concentration over the change in time. Or rate is equal to positive change in hydrogen iodide concentration over 2 times the change in time. And the 2 comes from the mole ratio of the original balanced reaction. Now I'm going to erase for just a moment. To talk more about order and what that means. When we write the rate law, we're expressing the relationship of all of the different reactants to rate. And so rate is equal to K, which is the rate constant, and you get this from the graph. Okay, so that's the rate constant. And we get this when we graph the data, which I'll show you later, times the concentration of hydrogen raised to some order times the concentration of iodine to some order. An order can be typically 0, 1, or 2. What that means in practical terms, for 0 order, rate does not change, so rate is constant as reactant is increased. Something that's first order, rate doubles as reactant concentration doubles. And if something is second order, rate quadruples as the reactant doubles. The only way for us to know these orders is to determine them experimentally. And it can be any order, it just depends on the mechanism of that particular reaction. All right, so let me erase for a moment. Let's look at some possibilities. All right, let's say that rate is equal to K times hydrogen concentration times iodine concentration. In this case, there is no superscript shown here, okay? So that means that it's first order. We don't show the 1, it's understood. First with respect to hydrogen, and first with respect to iodine. And then we add the orders together to get the order overall. So it would be second order overall, 1 plus 1. Or we might have the possibility rate is equal to K times hydrogen squared times iodine. Okay, so this would mean that it's second order with respect to hydrogen and first with respect to iodine. And then adding those together would be third overall. We could also have another possibility. There are several more. Say that rate is equal to K times hydrogen to the second order and iodine to the 0 order. Another way of saying that, anything to the raised to the 0 power is 1. So we would not have to include the concentration for that because it's just multiplied times 1. So rate is equal to hydrogen raised to the second power, second order overall. Okay, these are all possibilities. Again, I'm not going to know unless I do the experiment. We can actually solve for rate if we know some data about time and concentration of hydrogen in this case. Remember, if we're looking at this data, rate is equal to negative change in hydrogen over the change in time. Okay, so what is the average rate at 40 to 50 seconds? All right, I'm going to look at that there. It goes from, all right, so this is 0, 10, 20, 30, 40, 50. Okay, right here. That's 50 seconds. 10 seconds is the difference between them. And concentration goes from 0.0081 to 0.0067. Right, so I just subtract that 0.0014 and we plug and chug into our formula. Rate is equal to negative change in hydrogen over the change in time. Okay, so that's negative 0.0014 divided by 10 seconds. That's molarity, 10 seconds. Okay, so I just work the problem. And I get that the average rate for this time period is negative 0.00014 molarity per second. Let's look at some example problems. Right, first we'll look at this 2-hydrogen bromide, and the arrow is not shown. It goes to hydrogen plus bromine gas. And notice the relationship 2, 1, and 1. So we want to express the rate of the reaction in terms of change in concentration. All right, so I can write 3 different expressions here. Rate is equal to negative change in hydrogen bromide concentration over 2 times the change in time. Or rate is equal to the change in hydrogen concentration over the change in time. Or the change in bromine concentration over the change in time. All right, so I could use any one of those to solve problems. Looking at the second part of this question, in the first 25 seconds, the concentration of hydrogen bromide changes from 0.6 to 0.512. Calculate the average rate of reaction during this time period. So I want to use this formula right here to solve for rate. All right, so it's negative change in hydrogen bromide, so 0.6 minus 0.512 is 0.088 molar. Okay, so put that in there, 0.088 molar, divided by 2 times 25 seconds. Remember, we have to put 2 because our mole ratio tells us that there are 2. All right, so I do the math, and for 2 sig figs, I'm getting 1.8 times 10 to the negative third molarity per second. And we could put a negative in front here to indicate that it is being consumed during that time period. Right, for this example problem, first part, we want to write rate in terms of each reactant and product. So rate is equal to the change, negative change in A over 2 times the change in time, negative change in B over the change in time, or the change in C over 3 times the change in time. If I know that the change of A is 0.1 molar per 1 second, then B is 1/2 0.1 molar over 1 second. Okay, because A is twice as much as B, so we're going to divide by 2. That tells us that B is decreasing at a rate of 0.05 molarity per second. Then if I look at the how fast is C increasing, the change in B over the change in time is equal to the change in C over the change in time times 3. So we would multiply both sides by 3 here. In other words, 3 times 0.05 molarity per second is equal to 1.5 molarity per second. The last problem, problem number 3, we're asked to write the rate law for this reaction. We've got A, B, and C going to form products. So A plus B plus C goes to product. We know rate, our rate law, is equal to little k times some concentration of A some concentration of B and C to raise to some order. Okay, then I'm told additional information. It's first order with A, second order with B, and 0 order in C. So now I want to rewrite this to reflect those orders. Rate is equal to K times A to the first power, which we don't have to show that 1 there. It is understood, so I'll go ahead and erase that. And it's second order in B. And then in C, it is 0 order. Okay, so remember that that's the same thing as 1. This is our rate law. Right, so what is the overall order? It's 1 plus 2, first for A and second for B. So overall, it is third order. All right, then we're asked specifically, by what factor does the rate change if A is doubled? It's first order, so rate will increase by 2 times. Right? What about if B is doubled? B is second order, so rate will increase by 4 times. And by what factor if C is doubled? It's 0, or we could say 0th, and so it does not change. So I would just say 1 time there.